All right, welcome to week 11, our Salinity Sensor calibration week. We'll be discussing our Salinity Sensor circuit. It's an application of a 555 timer circuit, and we're going to use the changing water resistance to monitor salinity. We'll also discuss the programming. It's going to record the period between pulses. We'll discuss that more later. And we'll ultimately calculate the frequency and compare it from the period and then compare it to salinity. The last thing on this day is testing the valves. Similar to the heating week, we want to demonstrate that we can control salinity. So we're going to test the valve operation and then predict and verify a salinity change by adding a specific amount of one of the water sources to our sample. So let's move on here. So this is a little bit more detailed than you need, but we want you to understand what's going on. So this little drawing right here is a simulation of our water flowing through our salinity sensor. The sensor is essentially two probes sticking into a part of the tube that flows from our pump back around to the tank. In the water, as it gets saltier, the resistance will change. We have more ions available with saltier water, and so the value of resistance that water creates as it's part of a circuit becomes the important part that we're going to watch. Now, this resistance is tied together with a 555 timer. A 555 timer, when used in conjunction with a capacitance and a resistance, will create a pulsed output. So as we monitor the output of this timer, it creates a pulse based on how salty the water is. Now, a quick overview of that: more salt means more ions in the water, which means it's easier for electrons to flow, or the resistance is lower. Less salt, higher resistance. Similarly, when you're thinking about the period of these pulses, which is what we'll be measuring, it's the time between the pulses is the period. So more salt, we get a shorter period, a faster pulsed waveform. Less salt, a longer period, fewer pulses. So this is our key circuit. It'll be already assembled for you, but we want you to understand we're taking advantage of an electrical property to measure the salinity of our water system. All right, so taking a look at the salinity sensor circuit, again, the 555 timer shown here is this small integrated circuit right here. It's got 8 pins, and we're only going to use some of them. And those connections, again, we're going to go from the UNO 32 and provide 3.3 volts out to this pin. And so you can see that here. We're coming off the 3.3 volt power supply down to the board, and we provided 3.3 on this rail. We jumper from 3.3 over to pin 8, as it happens to be what that is, that back corner pin. All right. Again, on this ground is also coming in, so it's going to come off the UNO 32 and go to pin 1. So again, the ground, the black, comes over, jumps over to the rail here, and you can see this small black wire jumping to pin 1. Now, this capacitor is also installed next to pin 1, between pin 1 and 2, and then other wires here are made connections. So the salinity sensor is connected to pins 2 and 3, and you can see the blue and green coming out and making connection with the salinity sensor out on the tank. All right, so that's these white ones right here. They're coming off of pins 2 and 3. They're going up and going out to the salinity sensor. So we'll follow that. That's the brown cable here. Okay, so here's the salinity sensor coming in, and these two red and black wires are part of the salinity probe. So let me move my hand here. So the water flows up through this, and the two probes are sticking into the water stream. That's giving us our resistance measurement. Back to the circuit, there was one extra wire here. It's a jumper wire that connects pin 2 to pin 7 here. And so for us, it's shown in blue because it's all connected together. But on the board, it's this one yellow wire here. Now we pull, the final thing is where do we take our readings so we can look for those high and low pulses. The digital input on UNO 32 comes off of pin 3. And so pin 3 right here comes off, and we're going to connect it to digital input 2 over here on the UNO board. So that'll be our sensor input. That'll be the one we're looking for the pulses on. All right, so let's talk briefly about what's going on next for the sample preparation and then how to take the readings and take your data. So one of your homework assignments is to prepare 6 samples They're 300 milliliter samples. That's about the volume of the tank, which you found during week 10. We've got 0.15% salt water and DI water, or close to DI, and you have to prepare these samples. So we're going to show you one sample preparation method, and then you guys will prepare the rest. Then we'll show you how to move on to the next step. The next step is reviewing the program for sensor readings, and then finally we'll review the data sheet and the data collection piece. All right, so we're going to go ahead and mix up one of the samples for this week. I've got the 0.05% salt. In this case, I'm going to need about 200 grams. So I'm watching the scale. Going to get close. 70, 80, 90, 120, 130, 150, 160, 90. Oh, a little bit over. All right. I'm going to pull out just a little bit. And a little bit too much. About half that back in. 200. All right, so that was just DI water. I had extra DI that I used to start filling it, and this is our stock that we're using. Now I'm going to need the 0.15. I need 100 grams to finish out our 300 sample, so I'll pour it in until I get close to 300. I'll try not to overshoot this time, otherwise we'll contaminate things. So we'll stop there. Need 13 more. Each syringe is about 10 milliliters, so we'll start with this. Yep, another 3. Maybe about there. All right, so there's our 0.05 sample made from our DI and our All right, so after mixing up your samples, you'll have the DI water, the 0.05, the 0.075, 0.125, 0.1, and the 0.15. So get these samples all prepared, and then you're ready to go. Let's take a look at the program. All right, so let's talk about the UNO 32 programming for this case. Remember, we've got a pulsed waveform that we're going to be measuring. So we've got a digital input that's monitoring whether this is high or low. And so the program is going to take advantage of that high and low waveform. It's going to use a new command, a digital read, and when it sees a high, it's going to record the time. And then when it sees another high, it's going to record the time. Or in this case, I guess we're actually using lows. We'll take a closer look. All right, so and then it's going to return those values of period. So let's take a look at this. It's going to find the first time, and the second time, and then subtract them to get the period. Then in our program, we have a formula for calculating the frequency, and they're inversely related. So time is in seconds, but frequency is going to be in cycles per second, so how many pulses happen each second. And so the units for that is in hertz. So hertz are cycles per second. So this is the program. Let's take a look at the program real briefly and then watch it run. So you can see that we've set up pin 2 to be our salinity sensor, and we check that. And then it comes in, takes the salinity reading, switches it to measure in frequency, and also switches it to kilohertz by dividing by 1,000. And then of course it's going to print out the values that we're recording. Similar to last week, we've got a non-calibrated y equals mx plus b formula that you'll need to modify after you've collected your calibration data. So this down lower, if I scroll down, I'll show you a quick look. Not important, but you should see it. This is the section of the program that measures the period. It waits for a high and then a low, records a time, and does the same thing one more time. And you can see down at the bottom here, it returns the stop time minus the start time, which is the period. All right, so let's go ahead and start the program, run the serial monitor. This has been uploaded already, so we'll run the serial monitor and you'll see the screen pop up. I have it nice and long so we can watch the data trend on the screen. So you can see we're not getting any readings right now, and so there's a unique reason for that. Let's talk about that. All right, so what's happening with the computer hanging up and not producing any data is the tank is empty. So we're going to start with our DI water, which is our first sample for today. We're going to add it in, and we're going to need to get the water running. So we're going to get the pump running. Okay, got most of the bubbles out, so that is what you should have. We've got DI water in there running. All right, so we've got, you can see we just started collecting about 15 pieces of data here, and it's reading, let's see, it's 0.05%, which is not calibrated, and it's given us a kilohertz reading of 0.011 kilohertz. You'll notice as we look at the data arriving here, the time is in microseconds, and we're showing about 87,000 microseconds. The DI water is very non-conductive, but it's not ideally non-conductive. So we're going to get a number there, and it's getting inverted to create frequency. We took our first sample of data. We're going to do the deionized water. And the salt mass, ideally it's 0. In practice it's probably not 0 for the percent salt. But we had 87,000. And we also noticed that this formula is going to calculate it for us, but the one that we read on the screen was 0.11 kilohertz. This calculated cell will help you verify that you're doing things correctly. So if you're seeing a discrepancy, it may be that you're recording data in the wrong place. All right, so we're going to stop our pump and get ready for the next sample. We're going to pull the tank free, let that drain out. Empty the tank a little, let the pump come out a little bit. Move the heater, we're not really using it this week. As long as we're not turning it on, it'll be okay. Drain this out. And as it drains out, we're going to wipe it down. Having a good clean tank is important, so we'll just push the water out and wipe it out, and that'll be good enough. So we reassemble the tank with the flow loop, pour in the new sample of 0.15%, get the pump started, make sure and get rid of some of those bubbles, test it a couple of times. It's running nice and clean, and we'll go take a new reading. So we've left our program running, changed our sample, and we can see we're getting in values of time at 961, maybe 950, about 950 microseconds. So I'm going to write that down here for maximum salt, 950, and the approximate frequency is 1.05 kilohertz. Again, those formulas will invert this and calculate the frequency, and so it's a good check for you. Now again, this data is the frequency and the percent salt, and I'll put that here as well, the highest salt we have. You'll fill in the blanks with your samples and then make the two graphs and determine which trend lines and equations you should be using for your calibration. Once you're done, edit the calibration and have your two graphs, and you're set to go. All right, so again, for your calibration, you're going to create two graphs, frequency versus percent saline, percent saline versus frequency. Add your trend lines and determine which y equals mx plus b is applicable. Insert the values into the program and test the resulting serial monitor output. Finally, you'll want to change the calibration so that it says calibrated. All right, so just like week 10, in week 11 we're going to test our ability to control the salinity level. So that means we have to test our valves to know how much water they add, or how much water they add in order to change the salinity. So item 1 is to complete a flow rate test on each valve. So we're going to determine how many milliliters per second flow through the valves when we're doing. So you've got a data sheet like this, and we've got valve 1 with 3 test samples and valve 2. We're going to go ahead and do 3 samples on valve 1 here and show you how to complete this operation. All right, so we're going to go ahead and fill up our deionized water tank. And pretty full. And again, that's going to run down through the valve, and it normally goes into the tank. We're going to get it to run down into the cup. So we're going to modify our program to operate for 2 seconds, 4 seconds, and 6 seconds. All right, we're going to provide a second piece of code that allows us to take an initial reading of the salinity level and then operate the valve for a fixed amount of time. We're going to change it to 2 seconds, then we're going to use 4 seconds and 6 seconds. That's how long the valve operates. We send the valve pin for the DI high and then low. And so we'll run this program each time to drain water through the valve. We're going to run it a few times to start with to fill the lines, and then we'll run our tests. All right, so again, we've got deionized water up in the top. It's going to run down through the valve. So every time I press reset on the Uno 32, it's going to run water. You can see we have a small air bubble here. We're going to try and get rid of that. You can't always get rid of it, but we're going to make an effort. I'm going to recycle the program to drain water out. It's going to have the usual wait time, and then so again, we lost the bubbles there pretty well. So right now, keep running it until you get it emptied out, and then we're ready to do our test. In our case, we've done it a couple times already, and we're ready to do our next test. We're starting with an empty cup. In this case, the mass of the cup is 9 grams. We'll cycle the 2-second delay on the valve and capture the water. All right, so from this sample, we'll go weigh this mass, and I suspect it's going to be a few grams. So on the data sheet, we'll do a 2-second test, and if we subtract the mass of the cup, I suspect it's going to be about 4 grams. Change the program to do our 4-second trial. I'm going to hit the reset button. You'll see the DI water valve operation start here, and you'll hear the click in the background. We'll capture the water there and measure that mass as well. Press this, wait for about 4 seconds. 1, 2, 3, 4. And we've captured the water, and we'll weigh that to take our other piece of data. So using that, we did 4 seconds, got about 8.1 grams. We'll do another trial and get that value. You'll repeat that on valve 2. All right, so once you've completed your valve test, you'll know how long to operate the valves to make a particular salinity change. So the next step in this is to demonstrate that ability to control. So we're going to determine how long to open the valves to add 20 milliliters of either of the DI water or the saline to the tank. So on your program, we'll take a closer look at this in a second. We're going to use the spreadsheet to predict the change. Okay, so it means you'll need to measure the salinity in the tank using your new sensor, modify the program to open the valve for 20 milliliters of water of whichever source you're going to add, and then test that theory out. All right, so before the end of class, here's what you'll need to have done. The two graphs for the salinity calibration. Again, this week you'll be choosing which trend lines to use for the calibration and modifying the program to read salinity correctly. And then the last thing you'll do is complete that data sheet that includes a predicted change for salinity given some starting salinity value. You're going to add a certain amount of adding either DI or saline, and then what the volume is you're going to add and what that new salinity value is. So let this do the math for you. Figure out the formulas in here, and then do the test and find out what the actual salinity change. So this set here will be a completion of your work for the week.